Hello, everyone. We're going to go ahead and get started on section 10.1 today, which is on the basic concepts of probability. So as an overview, walking into a casino without knowing anything about probability is like coming empty-handed to a stick fight. Definitely doesn't put you in a very advantageous position. The study of probability came from an effort to understand games of chance, like any games that use dice, coins, or cards. So we have, little cartoons, someone yelling at one of the machines at a casino, getting very upset, probably doesn't know probability very well. And then we have a little dog playing some games with cards here, and he's saying, I have no idea what I'm doing. So hopefully by the end of this section here, you'll have a little bit of a better idea than this man or the dog. So, all right, starting out with sample spaces. So processes like flipping a coin, rolling a die, or drawing a card from a deck are called probability experiments. Probability experiment is a process that leads to well-defined results, which we call outcomes. An outcome is the result of a single trial of a probability experiment, so just any outcome, any result. And a sample space is a set of all possible outcomes of a probability experiment, so all the possible things that could happen. Then an event an event is a subset of the sample space of a probability experiment. So something like we would say an experiment would be like flipping a coin. The sample space would be head and tail, or heads and tails. So when you flip a coin, it's either heads or tails. Those are the only possible outcomes. When you roll a die, the only possible outcomes are rolling a 1, a 2, a 3, a 4, a 5, or 6. Those are the only possible outcomes. So those would be our sample spaces. An example of an event would be something like the sample space when you flip heads. So an event would be flipping heads, which is really just one of the two options. Another event could be something like, I'm going to roll a die and I want an even number. Even numbers on dice are 2, 4, and 6, which would be about half of your sample space. Or maybe an event is I want to roll a 1, which is just 1 out of your sample space. So those are events. Events are specifics. So typically a goal. So an event would be a very specific outcome given out of your entire sample space. So out of all of the different outcomes, you're looking for specific outcomes, and those are events. So that's how we kind of break down sample spaces in probability. So moving on to theoretical probability, we see the first type of probability that we'll study is theoretical probability. So the goal is determining the likelihood of an event without actually doing any experiments. So thinking to yourself, I'm rolling a die, I want to roll a 1, what are the odds I actually roll that? In theory, it should be 1 out of 6. There's only 6 options, and rolling a 1 is only one option out of 6. So that in theory would be 1 out of 6. But if you actually took a die and rolled it 100 times, you would realize that the number maybe isn't exactly 1 over 6. It's just that it, in theory, should be 1 over 6. So that's what we're going to study first, that theoretical probability of what should it be in theory. So if a specific event is occurring is E, we label E a lot with a specific event, then the complement of E would be E with an apostrophe, and that would be the event E not occurring. So E complement would be something like if E is I want to roll a 1 on a die, then the complement would be rolling anything other than a 1, which would have a much higher possibility. So the formula for theoretical probability that we're going to use, we're going to let E be an event in a sample space S, where N of E is the number of outcomes in that event E. N of S is the number of outcomes in your sample space S. So N of E is the number of outcomes of your specific event. N of S is the number of outcomes in your entire sample space. Then the probability of E is found as P of E, probability of E, is equal to the number of events in E, or the number of outcomes in E, divided by number of outcomes in your sample space S. And so it will be a ratio. This ratio is within 100% or 1 with fractions. So you can never have something like more than 1, really. You can't have like, oh, it's 150% possible. So going to be under 100% or in fraction form under 1. Now we have probability of a complement. So for any event E, if E complement is the event that E does not occur, then really we can find the probability of E complement by subtracting the probability of E from the value of 1. If the probability of E is a fraction, then we use 1. If probability of E is a decimal, we could even change that into percent as well. So 1 in fraction is the same as 100% in percent. So if you have a probability that's given to you in a percentage, you could also calculate this by using 100% minus the probability in percent. So that's how we calculate theoretical probability. So let's do a couple together. So for our example here, we have 2 coins are flipped. What's the sample space? So we're going to identify what the sample space is of our 2 coins being flipped. So we're going to say H is heads and T is tails. So our sample space, as a reminder, is the set of all possible outcomes. Sequential order does not matter, or the the order in which you write them in the sample space doesn't matter, but it does matter for this case since there are 2 options. It matters if like coin 1 is heads and coin 2 is tails versus coin 1 being tails and coin 2 being heads. So the order basically like between the commas when you list them, like that doesn't matter, but the order in which like the 2 coins get flipped does matter. So like heads, tails is different than tails, heads in this case. So it's something to keep in mind. You have 2 coins, you think coin 1, coin 2, and whichever one they flip, it will kind of change there. So when flipping 2 coins, you can flip 2 heads or you can flip 2 tails. We can label that as HH and TT for heads, heads, tails, tails. So they can match. In that case, since they match, it doesn't really matter if coin 1 or coin 2 was heads or tails. They were both the same, so that part doesn't really matter. But you could flip a heads, then tails. So flipping coin 1 would be heads and coin 2 is tails. Or you can flip tails, then heads. So coin 1 being tails, coin 2 being heads. And that changes it from HT to TH. So those 2 are separate. Those are different outcomes. Although, when we write it in our sample space, however way we arrange those doesn't matter. So those are all the different variations that can happen when you flip 2 coins. So we'd say our sample space is really going to be heads, heads, tails, tails, heads, tails, and tail heads. You could rearrange these. You could write, tails, tails, heads, tails, tail heads, heads, heads. The order within the brackets and how you separate them with the commas doesn't matter. But like we said, HT versus TH, there is a difference. Heads then tails, tails then heads. So those 2 are different. So the sequential order within an outcome does matter. So one thing to keep in mind. All right, so once again, 2 coins are being flipped. Now we're going to find the probability of getting 2 heads. So we already know the sample space because we found that on our last question there. We said our sample space was heads, heads, tails, tails, heads, tails, tail heads. So if we want the probability of getting 2 heads, really we're looking for heads, heads. And when we find probability, we want to find the number of outcomes. So the number of outcomes in our set would be 4. And our event is having 2 heads, so the heads, heads outcome. That's only 1 outcome. So the number of outcomes in set E would just be 1, because it's just heads, heads. So our probability is going to be, all right, there we go. Those numbers were switched there for a second, so I had to switch those back. So the probability of our situation here would be the number of elements in E, our event, divided by the number of elements in the whole subset. We know that the number of outcomes in our event is just 1, and the number in our whole subset would be 4. So the probability would be 1/4. So about a 25% chance. That's how we can calculate the probability. So another example, once again, 2 coins are flipped. We're going to find the probability of getting at least 1 tail. This is worded a little bit differently. Of course, we're still going to identify the sample space, and the number of elements in the sample space is 4. With E, our event that we're looking for, we want at least 1 tail, meaning that in our outcome, there should be at least 1 T listed. At least, meaning that you can have more than 1. It just needs to be at least 1. So really, these options are tails, 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 heads, and heads, tails. All of those have a T. The only outcome is heads, heads that isn't included. So the number of elements in our event E is going to be 3, the number of outcomes. So just like before, we can go ahead and put that together. The probability of our event would be equal to the number of outcomes in our event divided by the number of outcomes in our sample set. So we end up with 3/4, so 75%. So we have a 75% chance in this case that you get at least 1 tail. Now another example, this is a little different. We say your odds of being a contestant at The Price is Right is 2.8%. What are the odds that you do not get picked as a contestant? So our event that we're looking for here is being picked as a contestant for The Price is Right. That is the specific event that we have a percentage for. So E complement is not being picked as a contestant for The Price is Right. So we had E complement, the event itself was picked as a contestant, so complement would be not picked as a contestant. And we're told that the probability of the event, the probability of being picked as a contestant for The Price is Right, would be 2.8%. In decimal, we would write that as 0.028. So our probability of not being chosen as a contestant for The Price is Right would be the same thing as 1 minus the percent or the probability of being picked as a contestant, which we know is 2.8% or 0.028 in decimal. So we can go ahead and plug in our answer there in decimal. Like we said before, we can use 1 as 100%, or we can convert it to decimal and keep the 1, or we can use fractions and keep the 1. In this case, we use decimal and we kept the 1. So this comes out to 0.972, or in percentage, that would be 97.2%. So the odds that you do not get picked as a contestant are definitely much more likely at 97.2% versus your odds of actually being picked as a contestant, which is 2.8%. So remember, when you do complements, it's always going to be kind of the opposite scenario. So what is the chance that you don't get picked in this case? And that would be the whole, which is 1 or 100% minus the percent of that actual event happening. That leftover would be the not portion. So you not getting picked as a contestant would be what was left over. So, all right. Those were a lot of examples. We're going to do another one, but this one we're going to do together. We say a single die is rolled for the events listed below. We want to compute the probability and put the events in order from least to greatest. So for A, we have roll a 5. For B, we have roll a number more than 4. C, we have roll an odd number. And D, roll a 1 or a 6. So let's go ahead and do this all together. For our scenario here, it will help with first identifying what the sample space of our situation is going to be. So in the sample space would be all the different sorts of outcomes that you can end up having. So for example, rolling a single die, when we roll that die, the outcomes can only be 1, 2, 3, 4, 5, and 6. Those are the numbers on the die. So our sample space here would be all of those outcomes. 1, 2, 3, 4, 5, and 6. We don't care about any sequences in this case, so we're not worried about rolling a 1 and then a 6, or a 3 and then a 4. or anything like that. So we don't have to combine them in any way at all. We just write out all the different options. So we have 1, 2, 3, 4, 5, 6 as all the different outcomes. This means the number of outcomes in our sample space would be 6. So n of s would be 6 in this case, because there's only 6 outcomes. Now we can go ahead and start working on each individual event that we're looking for. So for A, we want rolling a 5. So if E is roll a 5, then the only outcomes for E would be a 5. That's the only thing we're looking for. One option, rolling that 5. So in our sample space here, we'll just write 5. So the number of outcomes in our event E would be 1. So in this case, we're going to find the probability of this situation rolling a 5 would be, as always, the number of elements in the event, or the number of outcomes in the event, divided by the number of outcomes in the whole sample space. And in our case, n of E is 1, and n of S is 6. So the probability would be 1 over 6. We're going to go ahead and leave that in fraction form. We're not going to convert to decimal or anything like that, so we can just leave that. So 1 over 6. Now for B, we want to roll a number more than 4. So E, roll a number more than 4. So our event, if we want to notice, it doesn't say 4 or more. We're saying more than 4. So that only leaves us with the numbers of 5 and 6 within our sample space. So our event would be 5, 6. There's only 2 outcomes, meaning that the number of elements in our event is 2. So just like last time, we're going to put that together. Probability of this event for part B would be the same thing, number of outcomes in our event divided by number of outcomes in the sample set. So the number of outcomes in our event was 2. Number of outcomes in our sample was 6. Now for these, we do want to simplify if we can. So in this case, 2 over 6 is the answer, but we can simplify that to get 1/3 as well. So we have the probability of rolling more than a 4 would be about 1/3. So moving on to C. For C, we want to roll an odd number. So roll an odd number. So we know on a die we can only roll 1 through 6. So our odd numbers will be 1, 3, and 5. So in this case, the number of outcomes that are possible are 3. So putting this together, just like every other time, we have probability of this event is probability of the outcomes in the event divided by the number of outcomes in the sample space, which leaves us with 3 over 6. Like we said before, we can simplify this if we can. So this would be 1/2. So this would be a 50% chance if we wanted to put it in percent. 1/2 would be half of the outcomes, which is 50%. Then lastly, we have D, which is not roll a 1 or a 6. So if we notice we have the word not there, we can certainly say our event is to not roll a 1 or a 6, and we can find what elements that would be. But since we see the word not, this really indicates opposite, which also indicates having more of a complement type of situation. So if we have not roll a 1 or a 6, we're talking about the complement. So we can go ahead and make a note of that here. So this one will use a complement. That means that our event E would be rolling a 1 or a 6. So in this case, we would have that E has two outcomes, 1 or 6, which in this case would mean that the number of events would be 2. We already have an example like this, so we can probably tell where this is going already here. But so we have probability of E, because remember we want to find the probability of E so that we can find the probability of E complement from that answer. So the probability of E, like always, N of E divided by N of S. So this would be 2 over 6. Now we know that this is 2 over 6, or in other words, 1/3, but since we're calculating a complement, it's a better idea to kind of keep our answers unsimplified and then see if it simplifies later instead of simplifying now and plugging that value in. In theory, they're going to equal the same answers, but we just want to keep that in mind. So we're going to stick with our 2 over 6 here. And now we want to find the probability of the complement. We say probability of E complement would be 1 minus the probability of E, which remember we want to find E complement would be not rolling a 1 or a 6, which is what we're going to find out here in a second. So P of E complement, the probability of E complement is 1 minus the probability of E, which is really 1 minus 2/6. Now, we have a fraction in this case. We have a whole number 1. So we want to express 1 as a fraction in order to actually simplify. So 1 is the same thing as anything over itself. And in order to subtract these terms, they have to have the same denominator. So I can rewrite 1 as 6 over 6. So I get 6 over 6 minus 2 over 6. And now I just subtract straight across. So 6 minus 2 is 4. And I keep the same denominator. So this is 4 over 6, which we can simplify. This would become 2/3. That would be the probability in this case of E complement. So the probability of not rolling a 1 or a 6. So we successfully found the probability of all these different outcomes. Remember, we want to lastly put these in order from least to greatest. If we look at our values here, we can compare our answers for when they're over 6 because they don't all have the same denominator. But so at the top for A, we had 1 out of 6. B, we technically had 2 out of 6. 3, C, we had technically had 3 over 6. And D, we had 4 out of 6. These are actually already in order from least to greatest. So we have here that this is least, and this one is greatest. And they're already in order. So from least to greatest, still it would just be A through D. Rolling a 5, then rolling a number more than 4, then rolling an odd number, and then not rolling a 1 or a 6. So that's the order that we would have. They're already in order. This is great. So, all right, let's go ahead and head on back over to our lecture. All right, so continuing looking at theoretical probability, We have some helpful observations about probability that help us to start kind of giving us a little bit more of an understanding. So we have a couple facts here. We say number one, probability is never going to be negative. The smallest probability you can have is a 0%, which would be an impossible scenario. Probability is also never greater than 1. You cannot have something that's like 150% certain or anything like that. Can't be greater than 1. If it's 100%, that is going to be, it is certain to occur. It's absolutely going to occur. 3, when an event can't possibly occur, probability is 0. When an event is certain to occur, the probability would be 1. If you add probabilities for every outcome in the sample space, the result always has to equal 1. And that's because if you take all of your outcomes, if you add together the probability of every single outcome occurring, it will become 1. Every outcome will have to occur at some point. So all of those add up to a full 1 or 100% if it's in percent. So I have a little chart here. So you can see 0 is impossible. Anything between 0 and 0.5 is probably pretty unlikely. At 0.5, that's the 50-50 mark. So, half and half. Anything greater than that 50-50 mark is likely. So it's very possible, very likely to happen. And then at 1 exactly, it is certain. It will happen. It's got that 100% like guarantee to happen, to occur in that case. So those are just some helpful observations you can have about theoretical probability. So if you're ever calculating probability and you get a negative number, that's not possible to begin with. So definitely something went wrong. Having a number greater than 1, that cannot happen as well. So that's definitely not not it. So that definitely can kind of affect your work. And then just knowing really what 0 and 1 mean within probability, and then knowing that if you add them all together, they should all equal 1. All the different outcomes added together would equal 100% of the outcomes. So just some helpful facts. We want to quickly recall sets. We've already been talking about sets a little bit, but it's important to kind of review a little bit here. So we'd say the theory of probability is related to the theory of sets that we actually learned in chapter 2, which was quite some time ago. For a probability experiment, the sample space is considered the universal set, and event E is called a subset of the universal set. So the event happening is just a subset of all the outcomes. As an example, when rolling a die, the sample space, aka the universal set, would be 1, 2, 3, 4, 5, 6. Those are all possible outcomes. If E is the event of rolling an odd number, E would be 1, 3, and 5, which is only about half of the actual outcomes. So we have a picture here. Our universal set would be all the options here, 1, 2, 3, 4, 5, 6. So E is that event of rolling an odd number. E complement would be rolling an even number in this case. And our universal set makes up all of the different outcomes. We also say that the union between E and E complement equals the whole universal set, and the probabilities added together will equal to 1. They're both 50-50, so adding those together comes out to be 1. So these are all just kind of reiterating things we've already stated and already established, but we can relate these two sets as well in kind of that set theory that we learned back from chapter 2. So as an example, we say, what's the event of pulling a heart face card from the deck of cards? So we want the cards from a standard deck, which is just going to imagine a standard deck of cards that have heart cards and they have face cards. We want to just remember or recognize that face cards are going to be Jack, Queen, and King cards. They're cards that have faces on them. We know that in a standard deck is broken up into 4 suits, one of those suits being hearts. And they're broken up evenly. A standard deck has 52 cards, and there's 4 sets of them, so there are 13 cards in each suit that you have. So if E is pulling, or the event of pulling a heart face card, that's going to be the face cards that are also of the heart suit. So the face cards are only the Jack, Queen, and King cards, and these will be also the heart cards, meaning that our event space here would be the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So it's the face cards that are also going to be heart cards as well. The face cards are found in every suit. Heart cards are found ace through 10, and then the face cards. So the combination of those would be face cards that are also heart cards. And in this case, there's only 3 options. So just another example. Then we can finish up here with empirical probability. The second type of probability that we study is called empirical probability. This is based on observed frequencies or the number of times a particular event has occurred out of a certain number of trials. So this is actually trying out, actually having experience or experiments, as opposed to just in theory, what should this be? So theoretical probability was that whole I roll a die, I want a 5, how probable is that? In theory, it's 1/6. But if we roll the die a bunch of times, we may not actually get 1/6. It may not actually be 1 out of 6 times. Maybe more than that sometimes, maybe less than that sometimes. The idea is that for theoretical probability, if you took an extremely large amount of experiments, the numbers should be very, very close. So theoretical probability and empirical probability, you will get closer in empirical probability to theoretical probability the more experiments that you actually conduct. The more times you actually try this experiment, the closer and closer you will get to theoretical probability. So anywho, that's what empirical probability is. It's the actual experiments. It's actually trying it out. So our formula for empirical probability, we say E is an event. The probability of E would be equal to the observed frequency of the specific event, which we can call F, divided by the total number of trials that you did, which was N. So you count how many times that event actually occurred, and you divide that by the total number of trials that you made. So for example, the information can be written in the form of what's called a frequency distribution as well, which we'll definitely go over very soon. And it consists of events and their frequencies. So as a result, in our class here, we got a little chart here. We say observed frequency, a win was observed 60 times, while a loss was observed 40 times. Together, the total made 100 times that all the frequencies together made, and win was about 60 out of the 100, lose was about 40 out of the 100. Maybe, for example, the theoretical probability should be 50-50, but it didn't actually end up being 50-50. It was more like 60-40. So those kinds of things will happen. You won't necessarily end up getting exactly the theoretical probability that you should be getting when you actually try out experiments. Because when you actually try out experiences, there's no guarantee that that will always be true. It is just likely or the probable of a certain scenario. So those are the differences between empirical and theoretical probability. So for our last example, we're going to roll some dice. The probability of rolling a 6 or less should be 5 out of 12 when rolling 2 fair dice, meaning just 2 dice that aren't unfairly weighted or anything like that. But we're going to see if we can actually get that probability by rolling 2 fair dice 12 times. So we're saying that the probability of rolling a 6 or less, so meaning adding those 2 dice up together, should be 5 out of 12. So we're actually going to take 2 dice, we're going to roll them 12 times and see if we can actually get 5 out of 12, meaning 6 or less, 5 out of 12 times, or maybe it's less, maybe it's more. We'll just see if we can actually do that. We're going to end up doing that 3 times just to get kind of a whole scenario here, see how many times we win versus lose. So let's go ahead and do that together. All right, so we have some dice and we're looking for wins and losses in this case. So wins are going to be rolling these dice and getting a 6 or less. And remember we said that this should come out to 5 over 12 times. So we're going to just make a tally mark every time we roll these dice and figure out if it was a win versus a loss. So a win being 6 or less, loss being 7 or more. So just more than 6 in this case. So we can go ahead and start rolling. So we take our dice and we roll. So we got a 5 and a 4, which is a 9. That is more than 6. That is a loss. So we'll go again. 4 and 3 is a 7, which is another loss. 5 and 5 is a 10, which is another loss. Whoop, this one slid off here, but a 6 and a 1 is a 7, which is another loss. So it's not looking good so far. 6 and 2 is an 8, which is another loss. So we've tried 5 times so far. Remember, we're doing this 12 times. A 3 and a 1 is a 4, which is less than 6. So there's a win. 2 and 1 is 3, so there's another win. 6 and 3 is 9, which is a loss. 5 and 4 is 9, which is another loss. 5 and 1 is 6, which is a win because we're saying 6 or less. 4 and 4 is 8, which is a loss. And one last time, 5 and 2 is a 7, which is another loss. So in this case, we ended up with 3 wins and what ended up being 9 losses. So in this case, this was only a 3 out of 12 that the scenario actually worked out. The goal was, remember, 5 out of 12. So we did not win the scenario. We lost this scenario. So this was not a successful scenario since we ended up having way more losses than wins. We only got a 3 out of 12 probability in this case instead of 5 out of 12, which is what it should be. So this was a losing experiment. So we said we'll do it 3 times. Let's do it again. All right, so trying this again. Remember, our goal here is 5 wins out of 12 outcomes. So that would look like 5 wins and 7 losses. That would be the perfect kind of scenario here that we're going for. So let's go ahead and try again. So we've got 4 and 2, which is 6, which is a win. 5 and 2 is a 7, is a loss. 2 and 2 is 4, which is a win. 4 and 2 is 6, which is another win. 2 and 1 is 3, which is another win. 5 and 5 is 10, which is a loss. 2 and 1 is 3, which is a win. That's 5. So in theory, we would have to have only losses for the rest of the time to get it perfect. So let's try. That's a 6 and a 3, which is a 9. 6 and 6 is a 12. 6 and 2 is an 8. We're almost there. 2 more losses. Okay. 5 and 4 is 9. And 6 and 4 is 10. That makes 12 with 5 wins and 7 losses. So this was a perfect 5 out of 12 win in this case. So this was a very successful trial. We actually did get the 5 out of 12 exactly, which is perfect. So there we go. So in that case, that was a winning trial. We actually got 5 out of 12 wins in this case, being rolling a 6 or less. We said we'd do it 3 times, so let's do it 1 more time. All right, so here's our last trial. 1 more time. Remember, a win is a 6 or less. A loss is anything greater than a 6, and we're aiming for 5 out of 12 wins. So here we go. 2 and 1 is going to be 3, so that's a win. 4 and 5 is 9, which is a loss. 4 and 1, 3 and 1 is 4, which is a win. 4 and 5 is a 9, which is a loss. Woo. 5 and 1 is 6, which is a win. 6 and 4 is a 10, which is a loss. 3 and 1 is a 4, which is a win. 5 and 3 is 8, which is a loss. 6 and 3 is a 9, which is in a loss. 5 and 3 is 8, which is another loss. 3 and 1 is a 4, which is a win. One last one. 5 and 3 is 8, which is another loss. So here we go one more time. We got 5 out of the 12 for wins, which makes this trial another win. Our result that we actually got here was pretty unlikely that we ended up getting that exactly twice. Most of the time, it doesn't even get out one time. So this was great that we ended up with twice winning that by getting 6s or less and getting 5 out of 12s 2 times out of 3. So that was a really good trial that we did there. So there we go. So like we saw for the very first time, we didn't necessarily get that perfect 5 out of 12. That actually doesn't happen very often. That happens that way pretty often. We don't often get the actual exact result here, but we did twice. So that was great. We should go to the casinos now. All right, let's head on back to our lecture. And that finishes up section 10.1. So in section 10.1, we learned how to compute theoretical probabilities and how to compute empirical probabilities. So that wraps up our section. I'll go ahead and see you in the next one. Good luck at those casinos.